Hello guys, my name is Marius from MP Cybersecurity. Welcome to the third episode of our introduction to cloud security. So we will be discussing all about infrastructure protection. I based this episode mainly on AWS best security practices. So this is the second pillar of security integration in our cloud security. So essentially, first pillar we covered identity and access management, and now we'll cover all about infrastructure protection and how we protect our infrastructure in cloud. So we'll cover most of the best practices that align to AWS, and we'll explore how we can protect our infrastructure. I guess the main point I'm saying is that we align this to AWS, but it's can be used for Azure and GCP because these practices will showcase various methods of how we can secure our infrastructure, and most of the infrastructure are similar and shared between all of the three main clouds. They just have different naming conventions. So we'll explore the best practices, and let's dive right into it. So first of all, infrastructure protection, it covers two main pillars within it. We have protecting networks and protecting the compute. So within compute, as you can see, we have instances such as Amazon EC2. We have containers such as Amazon ECS. We have also serverless compute instances such as AWS Lambda, and we have edge and hybrid computing instances. So, infrastructure protection encompasses control methodologies such as defense in depth that are necessary to meet the best practices and organizational and regulatory obligations. Use of these methodologies is critical for successful ongoing operations in the cloud. Infrastructure protection is a key part of an information security program. It ensures that systems and services within your workloads are protected against unintended and unauthorized access and potential vulnerabilities. So, for example, you'll define trust boundaries, for example, network and account boundaries, system security configuration, and maintenance. So, for example, hardening, minimization, and patching. Operating systems authentication and authorizations, for example, users, keys, access levels, and other appropriate policy enforcing points, for example, web application firewalls and API gateways. So, as you all guys are aware, within AWS, we have regions, we have availability zones, we have AWS local zones, and AWS outposts. So make sure you are familiar with regions, availability zones, as well as local zones and AWS outposts, which are components of the AWS secure global infrastructure. So AWS has the concept of a region, which is a physical location around the world where we cluster data centers. We call each group of logical data centers an availability zone. Each AWS region consists of multiple isolated and physically separated availability zones within geographic area. If you have data residency requirements, you can choose the AWS region that is close to your desired location. You retain complete control and ownership of the over the region in which your data is physically located, which can be helpful for meeting your regional compliance and data residency requirements. So, as you guys all are aware, with GDPR presence and all of the other data privacy requirements, you can select where you want to store your data, where your workloads are processing the data, and that's where the concept comes from. So each availability zone has independent power, cooling, and physical security. If an application is partitioned across availability zones, you are better isolated and protected from issues such as power outages, lightning strikes, tornadoes, earthquakes, and more. Availability zones are physically separated by a meaningful distance, many kilometers, from any other availability zone, although all are within 100 kilometers or 60 miles of each other, so they are around 60 miles apart. All availability zones in AWS region are interconnected with high bandwidth, low latency networking, using fully redundant dedicated metro fiber providing high throughput, low latency networking between availability zones. All traffic between availability zones is encrypted, AWS customers focused on high availability can design their applications to run in multiple availability zones to achieve even greater fault tolerance. AWS regions meet the highest levels of security, compliance, and data protection. AWS local zones place compute, storage, database, and other select AWS services closer to the end users. With AWS local zones, you can easily run demanding applications that require single-digit millisecond latencies to your end users, such as media and entertainment content creation, real-time gaming, reservoir simulations, electric design automation, and machine learning. Each AWS local zone location is an extension of AWS region where you can run your low latency sensitive applications using AWS services such as Amazon EC2, Amazon VPC, and Amazon EBS, Amazon file storage, and even elastic load balancing in your geographic proximity to end users. AWS local zones provide a high bandwidth, secure connection between your local workloads and those running in AWS region, allowing you to seamlessly connect the full range of in-region services through the same APIs and toolsets. And then lastly, AWS Outposts bring native AWS services, infrastructure, and operating models to virtually any data center, co-location space, or on-premise facility. You can use the same AWS APIs, tools, infrastructure across on-premises facilities and all the AWS cloud to deliver truly consistent hybrid experience. So AWS Outposts is designed for connected environments and can be used to support workloads that must remain on premises due to low latency or local data processing needs. So these are the main constructs of networks and our compute protection. So we'll first of all start on exploring how we're going to protect our networks. So to protect our networks, we have to adhere to main 4 best practices. So as you can see, they are listed here. So we have to create network layers, we have to control traffic at all layers, automate network protection, and implement inspection and protection. So users, both in your workforce and your customers, can be located nowadays anywhere. So you need to pivot from traditional models of trusting anyone and anything that has access to your network. When you follow the principle of applying security at all layers, you employ a zero trust approach. So zero trust security is a model where application components or microservices are considered discrete from each other and no component or microservice trusts any other. So carefully planning and management of your network design forms the foundation of how you provide isolation and boundaries for your resources within your workload. Because many resources in your workload operate in a virtual private cloud and inherit the security properties, it's critical that the design is supported with inspection and protection mechanisms backed by automation. Likewise, for workloads that operate outside of the VPC, using purely edge services and or serverless, the best practices apply in a more simplified approach. So you can also refer to the AWS Well Architected serverless application lens for specific guidance, but we're essentially following the AWS Well Architected framework and its security pillar, how we're going to secure networks as well as our compute. So first, best practice is we create network layers. So let's dive into the network layers. So the way we can create our network layers, we can segment our networks with separate virtual private clouds, as in VPCs. We have to judge and make decisions whether we're going to use public or private subnets. We need to create subnets and VPCs for each separate network layer to create a network isolation. We also use Firewall Manager to manage our VPC security groups. We also use Web Application Firewall as well as CloudFront for CDN, and we can use API gateways for our APIs. So group components that share sensitivity requirements into layers to minimize the potential scope of impact of unauthorized access. So for example, a database cluster in your virtual private cloud with no need for internet access should be placed in subnets with no route to or from the internet. Traffic should only flow from the adjacent next least sensitive resource. Consider a web application sitting behind a load balancer. Your database should not be accessible directly from the load balancer. Only the business logic or web server should have direct access to your database. So our desired outcome of this is to create a layered network. Layered networks help logically group similar networking components. They also shrink the potential scope of impact of unauthorized access. A properly layered network makes it harder for unauthorized users to pivot to additional resources within your AWS environment. In addition to securing internal network paths, you should also protect your network edge, such as web applications and API endpoints. So the common mistakes that people usually make is they create all resources in a single VPC or a subnet. We shouldn't do that. Also, users normally use overly permissive security groups, which is again a big mistake. They also fail to use subnets, or they are allowing direct access to the data stores such as databases. So that creates a high risk. So components such as Elastic Compute Cloud instances or EC2, Amazon Relational Databases, AWS Lambda functions that share reachability requirements can be segmented into layers formed by the subnets. So consider deploying serverless workloads such as Lambda functions within a VPC or behind an Amazon API gateway. Also, AWS Fargate tasks that have no need for internet access should be placed in subnets with no route to or from the internet. This layered approach mitigates the impact of a single layer misconfiguration, which could allow unintended access. And for AWS Lambda, you can run your functions in your VPC to take advantage of the VPC-based controls. For network connectivity that can include thousands of virtual private clouds, AWS accounts, and on-premise networks, you should use AWS Transit Gateway. So Transit Gateway acts as a hub that controls how traffic is routed among all of the connected networks, which act like spokes. So traffic between Amazon Virtual Private Cloud and Transit Gateway remains on the AWS private network, which reduces the external exposure to unauthorized users and potential security issues. Transit Gateway interregion peering also encrypts interregion traffic with no single point of failure or bandwidth bottleneck. So we can use some of these features to make sure that we creating layers. So we can use a reachability analyzer to analyze path between a source and destination based on configuration. So reachability analyzer allows you to automate verification of connectivity to and from VPC connected resources. And note that this analysis is done by reviewing configuration. No network packets are sent in conducting this analysis. We can also use Amazon VPC Network Access Analyzer to identify unintended network access resources. So Amazon VCP Network Access Analyzer allows you to specify your network access requirements and identify potential network paths. Also, consider whether resources need to be in a public subnet. Do not place resources in public subnets of your VPC unless they absolutely must receive inbound network traffic from public sources. Create subnets in your VPC. So create subnets for each network layer in groups that include multiple availability zones to enhance microsegmentation. Also, verify that you have associated the correct route tables with your subnets to control routing and internet connectivity. Use AWS Firewall Manager to manage your VPC security groups. So AWS Firewall Manager helps lessen the management burden of using multiple security groups. And secondly, use AWS WAF, Web Application Firewall, to protect against common web vulnerabilities. So WAF can help enhance edge security by inspecting traffic for common web vulnerabilities such as SQL injection, cross-site scripting, and many more. It also allows you to restrict traffic from IP addresses originating from certain countries or geographical locations, so you can blacklist specific locations. You can also use Amazon CloudFront as a content distribution network. So CloudFront can help speed up your web application by storing data closer to your customers. You can also improve edge security by enforcing HTTPS, restricting access to geographic areas, and ensuring that network traffic can only access resources when routed through CloudFront. And lastly, use Amazon API Gateway when creating application programming interfaces. So API Gateway helps publish, monitor, and secure REST, HTTPS, and WebSocket APIs. The second best practice is control traffic at all layers. So we will discuss things like VPC security groups, Web Application Firewall, as well as Shield, Firewall Manager, how we do VPC peering, AWS Direct Connect, and VPN. So when architecting your network topology, you should examine the connectivity requirements of each component. For example, if a component requires internet accessibility inbound and outbound, connectivity to VPCs, edge services, and external data centers. A VPC allows you to define your network topology that spans an AWS region with a private IPv4 address range that you set, or an IPv6 address range AWS selects for you. You should apply multiple controls with a defense in depth approach for both inbound and outbound traffic, including the use of security groups, so stateful inspection firewall, network access control lists, subnets, and route tables. Within a VPC, you can create subnets in availability zone. Each subnet can have an associated route table that defines routing rules for managing the paths that traffic takes within the subnet. You can define an internet routable subnet by having a route that goes to an internet or NAT gateway attached to the VPC or through another VPC. When an instance, Amazon Relational Database, Amazon RDS database, or other service is launched within a VPC, it has its own security group per network interface. This firewall is outside the operating system layer and can be used to define rules for allowed inbound and outbound traffic. You can also define relationships between security groups. So for example, instances within the database tier security group only accept traffic from instances within the application tier, by reference to the security groups applied to the instances involved. Unless you are using non-TCP protocols, it shouldn't be necessary to have an Amazon Elastic Compute Cloud or EC2 instance directly accessible by the internet, even with ports restricted by security groups without a load balancer or CloudFront. This helps protect it from unintended access through an operating system or application issue. A subnet can also have a network ACL attached to it, which acts as a stateless firewall. You should configure the network ACL to narrow the scope of traffic allowed between layers. Note that you need to define both inbound and outbound rules. Some of the AWS services require components to access the internet for making API calls, where AWS API endpoints are located. Other AWS services use VPC endpoints within your Amazon VPCs. Many AWS services, including Amazon S3 and Amazon DynamoDB, support VPC endpoints, and this technology has been generalized in AWS PrivateLink. We will also recommend to use this approach to access AWS services, third-party services, and your own services hosted in other VPCs securely. All network traffic on AWS PrivateLink stays on a global AWS backbone and never traverses the internet. Connectivity can only be initiated by the consumer of the service and not by the provider of the service. Using AWS PrivateLink for external services access allows you to create air-gapped VPCs with no internet access and helps protect your VPCs from external threat vectors. Third-party services can use AWS PrivateLink to allow their customers to connect to the services from their VPCs over private IP addresses. For VPC assets that need to make outbound connections to the internet, these can be made outbound only one way through an AWS managed NAT gateway, outbound only internet gateway, or web proxies that you create and manage. So Amazon Virtual Private Cloud provides features that you can use to increase and monitor the security of your virtual private clouds, such as security groups. So security groups allow specific inbound and outbound traffic at the resource level, such as an EC2 instance. When you launch an instance, you can associate it with one or more security groups. Each instance in your VPC could belong to a different set of security groups. If you don't specify a security group when you launch an instance, the instance is automatically associated with the default security group for its VPC. Next one is network access control lists. So network ACLs allow or deny specific inbound and outbound traffic at the subnet level. You can also create flow logs. So flow logs capture information about the IP traffic going to and from network interfaces in your VPC. You can create a flow log for a VPC, subnet, or individual network interface. So flow log data is published to CloudWatch logs or Amazon S3, and it can help you diagnose overly restrictive or overly permissive security group and network ACL rules. You can also do traffic mirroring. You can copy network traffic from elastic network interface of an EC2 instance. You can then send the traffic to out-of-bound security and monitoring appliances, such as your SIEM and SOAR tools. A security group controls the traffic that is allowed to reach and leave the resources that is associated with. For example, after you associate a security group with an EC2 instance, it controls the inbound and outbound traffic for the instance. You can associate a security group only with the resources in the VPC for which it is created. When you create a VPC, it comes with a default security group. You can then create additional security groups for each VPC. Also note, there are separate security groups for the load balancer, for the web servers, and for the database servers. You can add rules in the security group for the load balancer to allow HTTP or HTTPS traffic from the internet. You can add rules to the security group for the web servers to allow traffic only from the load balancer. You can add rules to the security group for database servers to allow only database requests from the web servers. You can also use Web Application Firewall, Shield, and AWS Firewall Manager together to create a comprehensive security solution. WAF is a web application firewall that you can use to monitor web requests that your end users send to your application and control access to your content. AWS Shield provides protection against distributed denial of service attacks for AWS resources at the network and transport layers, so layer 3 and layer 4 of the OCI model, as well as the application layer, which is layer 7. AWS Firewall Manager provides management of protection like the AWS WAF and Shield Advanced across accounts and resources, even if the new resources are added. So let's explore the Web Application Firewall in a little more detail. So WAF lets you monitor the HTTP and HTTPS requests that are forwarded to your protected web application resources. You can protect resources such as Amazon CloudFront distribution, Amazon API Gateway, REST APIs, Application Load Balancer, AppSync, GraphQL APIs, Amazon Cognito User Pool, AWS App Runner Service, verified access instance. So WAF lets you control access to your content based on conditions that you specify, such as the IP addresses that requests originate from or the values of query strings. Your protected resources responds to requests either with the requested content or with an HTTP 403 status, which means forbidden, or a custom response which you can generate yourself. At the simplest level, WAF lets you choose one of the following behaviors. So allow all requests except the ones that you specify. So this is very helpful when you want Amazon CloudFront, API Gateway, Load Balancer, AppSync or Cognito, or any other application to serve content for a public website, but you also want to block requests from the attackers. You can also block all requests except the ones that you specify. This is useful when you want to serve content for a restricted website whose users are readily identifiable by properties in the web requests, such as the IP addresses that they use to browse to the website. You can also allow content requests that match your criteria. So you can use the count action to track your web traffic without modifying how you handle it. You can use this for general monitoring and also to test your new web request handling rules. When you want to allow or block requests based on new properties in the web requests, you can first configure the WAF to count the requests that match those properties. This lets you confirm that your new configuration settings before you switch your rules to allow or block the matching requests. You can also run captcha or challenge checks against requests that match your criteria. You can implement captcha and silent challenge controls against requests to help reduce bot traffic to your protected resources. Using WAF has a host of benefits, such as additional protection against web attacks using criteria that you specify. You can define criteria using characteristics of web requests, such as the following: IP addresses that requests originate from. You can verify the country that requests originate from, values in request headers, strings that appear in requests, either specific strings or strings that match regular expressions, patterns such as regex, length of requests, the presence of SQL code that is likely to be malicious, known as SQL injection, presence of a script that is likely to be malicious, known as cross-site scripting. You can also define rules that allow, block, or count web requests that meet the specific criteria. Alternatively, rules can block or count web requests that not only meet the specific criteria, but also exceed a specified number of requests in any 5-minute periods. You can also create rules that you can reuse for multiple web applications. You can also create get managed rules from AWS and AWS Marketplace sellers. You can create real-time metrics and sampled web requests, automated administration using AWS WAF API. And if you want a granular control over the protection that you add to your resources, WAF alone might be the right choice. Also, let's look at AWS Shield. So you can use AWS WAF, Web Access Control Lists, to help minimize the effects of the distributed denial of service attack. For additional protection against DDoS attacks, AWS also provides AWS Shield Standard and AWS Shield Advanced. So AWS Shield Standard is automatically included and no extra cost beyond what you already pay for your AWS WAF on your AWS resources. But AWS Shield Advanced provides an expanded DDoS attack protection for your Amazon EC2 instances, load balancers, CloudFront distributions, Route 53 hosted zones, and AWS Global Accelerators, standard accelerators. AWS Shield Advanced incurs additional charges, and AWS Shield Advanced options and features include automatic application layer DDoS mitigation, advanced event visibility, and dedicated support for the Shield response team. If you own a high visibility website or otherwise, you are potentially prone to frequent DDoS attacks, consider purchasing additional protections such as Shield. And then lastly, let's explore the AWS Firewall Manager. So AWS Firewall Manager simplifies your administration and maintenance tasks across multiple accounts and resources for the variety of protections, including AWS WAF, AWS Shield Advanced, AWS VPC security groups, AWS Network Firewall, and Amazon Route 53, the Reserver DNS Firewall. With the Firewall Manager, you can set up your protections just once, and the service will automatically apply across your accounts and resources, even when you add the new resources or new accounts. So the virtual private cloud is a virtual private cloud dedicated to your AWS account. So it is logically isolated from all other virtual networks in your AWS cloud. You can launch AWS resources such as EC2 and many others in your VPC. And lastly, a VPC peering connection is a networking connection between two VPCs that enables you to route traffic between them using private IPv4 and IPv6 addresses. So instances in either VPC can communicate with each other as if they are within the same network. You can create VPC peering connection between your own VPCs or a VPCs in another AWS account. The VPCs can be in different regions, also known as inter-region VPC peering connection. So imagine, guys, if you are, we talked a bit about, segmentation and splitting different layers, but there are potential requirements sometimes that you can create a specific virtual private clouds or specific VPCs where you host your databases. Maybe you have a front-end VPCs, maybe you have a middleware VPCs. So sometimes there will be needed a communication between various VPCs. And that's how we use VPC peering. So we can pair the virtual private clouds to create an interconnection between those VPCs. So AWS can use existing infrastructure of VPC to create a VPC peering connection. It is neither a gateway nor a VP connection and does not rely on separate piece of physical hardware. There is no single point of failure for the communication or a bandwidth bottleneck. VPC peering connection helps you to facilitate the data transfer. And for example, if you have more than one AWS account, you can pair the VPCs across those accounts to create a file sharing network. You can also use VPC peering connection to allow other VPCs to access resources you have in one of your VPCs. So when you establish a VPC peering relationships between the VPCs across the different AWS regions, resources in the VPC, so for example, EC2s and Lambda functions in different AWS regions can communicate with each other using private IP addresses. And that's, I guess, the key point. It's a private IP address communication, so it's not exposed to the public internet. And without using any gateway, VPN connection, or network appliance, the traffic remains in the private IP space. All inter-region traffic is encrypted with no single point of failure or bandwidth bottleneck. Traffic always stays on a global AWS backbone and never traverses the public internet, which reduces the threats such as common exploits, DDoS attacks. Inter-region VPC peering provides a simple and cost-effective way to share resources between regions or to replicate data for geographic redundancy. That's, again, a key point. If you're doing geographic data redundancy or geographic data backup, VPC peering will help you a lot. And then lastly, let's explore AWS Direct Connect. So this helps you to link your internal network to an AWS Direct Connect location over a standard Ethernet fiber optic cable. One end of the cable is connected to your router and the other one is to an AWS Direct Connect router. With this connection, you can create virtual interfaces directly to the public AWS services. For example, an Amazon S3 or to an Amazon VPC, bypassing the internet service providers in your network path. An AWS Direct Connect location provides access to an AWS in the region with which is it associated. You can use a single connection in a public region or AWS GovCloud for the government cloud base to access public AWS services in all other public regions. And then lastly, we have a VPN. So a VPN is a virtual private network. So essentially what we can use VPNs for our distributed workforce to privately connect to specific services in our cloud. So if we have, for example, organizations normally have vendors or third parties that might require access to particular AWS internal resources or services, we can establish an AWS VPN and connect over the private encrypted tunnels straight into the services. So this way we're not traversing the public internet, and the end-to-end is always encrypted. So it's a great way to reduce the potential threat and potential vulnerabilities that can be exploited in open public internet. So that's the control of traffic at all layers. So the third best practice is we need to automate our network protection. So we can do security automation using AWS Web Application Firewall. So we can automate protection mechanisms to provide a self-defending network based on a threat intelligence and anomaly detection. For example, intrusion detection and prevention tools that can adapt to current threats and reduce their impact. So a web application firewall is an example where you can automate network protection. For example, by using AWS Web Security Automation solutions, you can automatically block requests originating from IP addresses associated with the known threats. We can also automate protection for web-based traffic. So AWS offers a solution that uses AWS CloudFormation to automatically deploy a set of AWS WAF rules designed to filter common web-based attacks. Users can select from pre-configured protective features that define the rules included in AWS Web Access Control lists. Also, we can create a WAF security automation, so we can consider AWS partner solutions, and AWS partners offer hundreds of industry-leading products that are equivalent, identical to, or integrate with existing controls in your on-premise environments. So we can use the products and services to allow you to deploy a comprehensive security architecture and a more seamless experience across your cloud and on-premise environments. So as you can see in the picture, is greatly explained your AWS WAF managed rules and how we can deploy and how we can protect from various attackers in our environment. So let's explore some of the managed rules that we can deploy. So AWS, as you can see, the first is managed rules. So this set of AWS managed rules provides protection against exploitation of a wide range of common application vulnerabilities or other unwanted traffic. Then we have BNC, which is essentially manual IP lists. So this component creates two specific AWS WAF rules that allow you to manually insert IP addresses that you want to allow or to deny traffic. You can also configure IP retention and remove the IP expired addresses from these IP lists. Now, if we move down the line, we can see the F part, which allows us to detect the HTTP flood. So this component helps you protect against attacks that consist of a large number of requests from a particular IP address, such as web layer, distributed denial of service attacks, or a brute force login attempts. You can also set a quota that defines the maximum number of incoming requests allowed from a single IP address at the default 5-minute period. We can also detect scanners and probes. So this component passes application access logs, searching for suspicious behavior such as an abnormal amount of errors generated by an origin. It then blocks those suspicious resource IP addresses for a customer-defined period of time. We can also gather IP reputation lists. So this component is the IP list parser. So it's essentially a Lambda function which checks third-party IP reputation lists hourly for new ranges that we can block. I is all about bad bot. So this component automatically sets up a honeypot, which is a security mechanism intended to lure and deflect an attempted attack. And then lastly, let's explore the one that I missed. It's DNE, so SQL injection and cross-site scripting. So the solution also configures two WAF rules that are designed to protect against common SQL injection or cross-site scripting patterns in your URI, query string, or a body of a request. So this is the way that we can protect our applications from host of threats and host of potential attacks, and how we can manage allowed lists, deny lists, check IP reputations, and various common scripts that are, threat actors potentially can use against our applications. So it's a great way to leverage a tool that can help you be more secure. And then the last part of our pillar of network protection is implementing inspection and protection. So as you can see, this mainly built around Amazon GuardDuty. So it's a threat detection service that can continually monitor for compromised accounts, anomalous behavior, as well as malware. So you can inspect and filter your traffic at each layer. You can also inspect your VPC configurations for potential unintended access using your VPC network analyzer. You can specify specific, network access requirements and identify potential network paths that do not meet them. So, for components that transacting over HTTP-based protocols, a web-based application firewall also can help protect from common attacks, as we just explored, and how to monitor those and block those HTTP requests, that matched against configured rules. We can also explore, as I mentioned, WAF, the shield and advanced protections also. But the main part of this is we're going to configure how we, should deploy the Amazon GuardDuty. So GuardDuty, as I just mentioned, guys, is a threat detection service that continuously monitors for malicious activity and unauthorized behavior to protect your AWS accounts and workloads. So you can use GuardDuty and configure automated alerts that automatically notify you for potentially malicious or anomalous behavior. So how we deploy that? First of all, we need to configure virtual private cloud flow logs. So VPC flow logs is a feature that allows you to capture information about the IP traffic going to and from your network interfaces in your VPC. Flow log data can be published to Amazon CloudWatch Logs and Amazon Simple Storage Service, which is S3. After you created a flow log, you can retrieve and view its data in a chosen destination. So you can consider VPC also traffic mirroring. So traffic mirroring is a VPC feature that you can use a copy of network traffic from Elastic Network Interface, an Elastic Compute Cloud instances, and then send it outbound to the Amazon GuardDuty. So Amazon GuardDuty is a security monitoring services that analyzes and processes the foundational data sources such as AWS CloudTrail management events, AWS CloudTrail event logs, VPC flow logs from the EC2 instances, and also DNS logs. It also processes features such as Kubernetes audit logs, RDS login activity, S3 logs, EBS volumes, runtime monitoring, as well as Lambda network activity logs. So it uses threat intelligence feeds such as lists of malicious IP addresses and domains, machine learning to identify unexpected, potentially unauthorized and malicious activity within your AWS environment. This can include issues like escalation of privileges, use of the exposed credentials, or communication with the malicious IP addresses, domains, presence of malware on your EC2 instances, and container workloads. So, as well as potentially discover of unusual patterns of login events on your databases. So for example, GuardDuty can detect compromised EC2 instances and container workloads serving malware or mining Bitcoin. It also monitors AWS account access behavior for signs of compromise, such as unauthorized infrastructure deployments, like instances deployed in a region that hasn't been used before, or unusual API calls like password policy change to reduce the password strength. So GuardDuty informs you the status of the AWS environment by producing security findings that you can view in the GuardDuty console or through Amazon Event Bridge. GuardDuty also provides support for you to export your findings to an Amazon Simple Storage, which is S3 bucket, and integrate with other services such as AWS Security Hub and AWS Detective. So it's a great way to overview and see potential threats in your environment, to detect potentially, anomalous behavior and prevent threats before they become data breaches. So please make sure you are aware how to deploy, how to use Amazon GuardDuty. So that's pretty much it for this episode. We explored how we're going to protect our network interfaces and networks. In the next episode, we will explore second part of the security pillar of how we're going to protect our compute instances and compute environments. So thank you for your time, guys. Hopefully you learned something. Hopefully you enjoyed. Like and subscribe. Thank you very much.